341. In 6 we have f of x equals 1 over x squared. They're giving us x equals 1. They're giving us delta x equals 0.5, which we know is the same with dx. And they're asking us to find the dy and the delta y. So I know two definitions. Dy equals f prime of x dx. This is carved in stone. And also delta y is also carved in stone, is f of x plus delta x minus f of x. These are the definitions. We cannot change those. All we have to do is fill it in. Okay, so this function is the same with x to negative 2. So f prime of x will be negative 2, x to negative 3, or negative 2 over x to the third. Is this okay so far? So this is calculus, and this is algebra. So the calculus part is dy equals negative 2 over x to the third times dx. All I have to do is just plug in the numbers. I have negative 2 over 1 times 0.5. And this is negative 1. The delta y, again, I have to plug in the numbers. 1 plus 0.5, so this is f of 1.5 minus f of 1. You don't have to do this by hand, or you can do it with a calculator. You just have to plug them in. So I put the function in a graphing calculator. So in y equals, I put in 1 over x squared, which is right here. I think we did something with this last time. We did it again or something, I'm not sure. Let's see. Yep, 1.5 and 1. So all I have to do is subtract 0.4444 minus 1. And that's it. That's all you need to do. So this part is algebra, and this part is calculus. Once you use the formulas, you put the formulas there, you just plug it in. Any questions? Is this okay? Is that what we wanted to do, George? Okay, perfect. Anything else, other questions? Anything else comes to mind? Okay, so let's look at, since we are here and we have the book open on this page, let's find the linearization and the approximation and so on and so forth. Let's choose a problem from 19, 20, 21, 22, 23, 24, any problem, and answer those 4 questions. The linearization, which is the line that approximates a function near a number.
Could we do 24?
Of course. Let's work on 24. Excellent. So we are given a function, and in this case, the function is natural log. So this is 24 on page 341. And we have f of x equals natural log x. Find the linearization, which is L of x, at, they say, a equals e. Again, I have to remember the formula. The formula is f of a plus f prime of a x minus a. This is carved in stone. This is the formula. All I have to do is plug it in. Find f prime, plug in, plug in, plug in. That's it. So I have to find f prime of x. Can anyone give us f prime of x for natural log x? This should take a blink. Please.
1 over x.
Thank you very much. Excellent. Very good. So now, f of a is f of e, but I know that's 1. F prime of e, I know, I have it now, which is 1 over e. And x minus a, I know it. I know what it is x minus e. And that's it. I'm done. I just have to plug them in. So L of x equals 1 plus 1 over e, x minus e. I distribute, I have to. So I have 1 over e times x. 1 over e times negative e is negative 1 plus 1 is 0. This is it. What does this say? Again, on the graph of natural log x, let me graph it for you. We know the graph. We studied it in chapter 2. This is the graph of natural log x. When x is e, which is 2 point something, this is 1, 2, 3. So somewhere here, this is e. At this point on the graph, this line has this equation, L of x equals 1 over ex. So you don't have to graph any of this. I'm just explaining what this means. I graphed the function natural log x. I showed you where the point when x is e, and of course this is 1, is. At this point, I draw the tangent line, which has this equation. And now what I'm saying is, near this point, a little bit to the left of e and a little bit to the right of e, I don't have to use natural log x to approximate the function. I can use the line to approximate the function. But if you say approximate the function here, no, it's too far out. Here I have to determine another tangent, and then I will be able to use this tangent, but not this tangent, to approximate natural log near that point. That's all it means. Good. So now there is part B, C, or whatever else we have. Use a linearization to approximate natural log of 2.72. 2.72 is very close to E. How do I know? Here's how I know. Because here you have E. In case you forget, here's E right here. Second, and the division symbol, and that's your E. It's 2.718. And here we have, where is my book? Here's my book. Okay. So here we have 2.72. So I'm using the linearization to determine natural log, so this is part B, natural log of 2.72. So L of 2.72 is 1 over E times 2.72. It says use the linearization from part A to approximate this. So I plug in 2.72. It's close enough to E. So I can use the tangent, because if you say approximate using this tangent, approximate at 4 or 5 or 10, I'll say, no, I can't. This number has to be close to E, either to the left, a little bit lower, or a little bit higher to the right. So when I determine this approximation, I have 2.72 divided by E. So I get approximately 1.0006. Now, in part C, find natural log 2.72 using a calculator. So this will be the exact. So now they want us to find natural log of 2.72 using the function, not the approximation, not the linearization. So when I plug in natural log, when I plug in 2.72, I should get something close, very close to this, because the approximation should be very close to the real actual value. Look at this. 2, 4, 5 digits. Okay, very good approximation. So using the line is a very good approximation of the actual value. Part D, what is the difference between the approximation, so the approximation was, and the actual value? Almost nothing. So the difference is 1.00063208 minus 1.000631188. Almost nothing. So from this one, when I subtract, they want the approximation, but that's okay. I'm going to get the opposite number. That's fine. 1.00063208. It's almost nothing. So it's 1.996921 times 10 to negative 7. Nothing. That's the difference between the approximation and the actual. Any questions on this so far? Okay, so let's look at a few examples with related rates. Anybody has anything in mind with related rates? So I'm going to make a list of topics now. So topics for test 2. Number 1 that we just discussed, linearization, approximating a function using the tangent at that point, using a line at that point. Okay, so that's one question. The second one, related rates. So let's look at an example with related rates, and let me just come up with a page number. It's at the end of chapter 3. Related rates, this is 3.9, yes, page, 365. Okay. So let's choose a related rate situation. We worked on many problems. We used problems from the revenue, cost, and profit. We worked on something like this. Yeah, let's do this. 31 on page 365. So g squared plus h squared equals 25. What is the rate of change dh over dt when dg over dt is 3? G, they say, is 0. And then g equals 1 and g equals 3. It doesn't matter, you know, we don't need to do more than one value. So looking at the question, we realize that age is a function of what and g is a function of what, which is very important to realize. When we look at this and this, what do we conclude? That h and g are functions of h and g are functions of
Is it the time?
time or t, whatever it is. Yes. Thank you very much. When we have the notation when we look at the notation dH over dt or dg over dt, we know that h and g are functions of t. Normally t is time, but it can be temperature, it can be whatever. It doesn't matter. But yes. Good, which means that these are not variables. I'm going to put a dot underneath. They're not variables, they're functions. So now we have to differentiate implicitly, because they're asking us to find the derivative of h with respect to time given some information. So can anyone help with that? How do we differentiate both sides? Anybody, please?
25 is 0.
Say it again.
25 is 0.
Yes, the right-hand side is 0. The left-hand side.
For g, it's 2g times dg over dt.
Excellent. Plus.
Same thing for h, just remove the g.
H dH over dt. Thank you very much. In this situation, you can divide both sides by 2, and 0 divided by 2 is 0. And they're asking us to solve for dH over dt. So this is our variable. We're going to move, this is all algebra now. We're going to move this term to the other side and divide by h. So dH over dt equals negative g times dg over dt divided by h. So we have found the formula. Again, the next steps are just plain algebra. We just have to plug in the numbers we have. And we are going to plug in this, replace this with 3, and replace this with 0. And we do not have h, but that's okay. Because when g is 0, h squared is 25. So they're not telling us, but they should. So this will be positive, because remember, when we take the square root of 25, we get only positive, but if h is negative, then the answer could be negative. So if this is 5 or negative 5, it really doesn't matter. The answer will be 0. Why? 0 times 3 is 0. 0 divided by 5, no matter what the sign is 0. So I found an expression for the derivative dH over dt, which was really simple. And then all I had to do is plug in the numbers that were given to us. So if you only have, in this case, we only have, or if g is 1, then h squared is 24, and we take the square root. But they should tell us that g and h are positive numbers. So we don't have to worry about plus or minus. This was a problem on related rates. Any questions?
How was it you determined that h is 5 there? I can see, obviously we're given the 0.
If g is 0, h squared equals 25. How much is h?
Thank you.
Perfect. Good. So here's another question on related rates. Let's say I have a square. And I'm told, and as we know, the square has all sides equal. And let's say I'm told that the side is increasing at 10 millimeters per second. 10 millimeters per second. Side, so x is increasing at 10 millimeters per second. And the question now is, how fast is the area increasing when the side is, let's say, when the side is 20 millimeters. How do I start? What is the starting point? What do I need to do?